Video is titled Work and Energy with Springs. Question 1. State the equation for the elastic potential energy of a compressed or stretched spring. Define each variable. What is the meaning and units for the spring constant K? So E sub H stands for Hooke's law, equals 1/2 K delta X squared. K is a spring constant, has units of newtons over meters, and it tells us about the stiffness of the spring. So if K has a large value, then the spring is very stiff or strong. It's very difficult to compress that spring. If K has a small value, then the spring is very weak and it's very easy to stretch and compress that spring. Delta X is the distance a spring is compressed or stretched from its equilibrium position. Has units of meters. Question 2. A force of 35 newtons is applied to a spring, and as a result the spring stretches a distance of 12 centimeters. What is a spring constant K for the spring? They gave us F and delta X, so we could just solve for K. Part B. How much energy will be stored in this spring? We could use Hooke's law, 1/2 K delta X squared. Question 3. A spring which has a spring constant K is hung from the ceiling. A mass of 3 kilograms is added to the end of the spring and is then slowly lowered until equilibrium is reached. At this point, the bottom of the mass has been lowered a distance of 52 centimeters. Part A. What is the magnitude of the force being exerted by the spring when the system reaches equilibrium? So sigma F equals ma sub y. A sub y is 0. So sigma F is 0. We have plus force of the spring, Hooke's law, minus force of gravity equals 0. So it's equal to mg, which is about 29.4 newtons. Part B. What is the spring constant of the spring? F is equal to K delta X. Don't worry about the negative sign because we know that K is always going to be positive. So plug it in the values, we get about 56.6 newtons over meter. Part C. How much energy is stored in the spring when equilibrium is reached? Energy is 1/2 K delta X squared. 7.65 joules. Question 4. A mass of 5 kilograms is dropped from a height of 2.2 meters above a vertical spring sitting on a horizontal surface. Upon colliding with the spring, the mass compresses the spring 30 centimeters before it momentarily comes to a halt. Assume H is equal to 0 at the lowest points. So how much gravitational potential energy was contained in the 5 kilogram mass before it was dropped? Well, we're just going to use mg delta H. So what's delta H? It's 2.2 meters plus 0.3 meters. Part B. How much energy will be stored in the spring when the mass comes briefly to a halt? It's about 123 joules. Part C. What is the spring constant of the spring? It's 1/2 K delta X squared. And solve for K. Question 5. A horizontal spring with a spring constant K equals 30,000 newtons over meters compressed 6 centimeters by an 800-gram block, which is resting on a frictionless surface. The block is then released from rest. So part A, draw a figure. Part B, what is the initial potential energy of the spring? Just use 1/2 k delta x squared. We were given k and delta x. Part C, what is the kinetic energy of the block after it leaves the spring? So recall the law of conservation of energy. So we get 5.40 joules. Part D, what is the final speed of the block after it leaves the spring? We have this equation here. Energy initial equals energy final. Part E, after some distance, the block moves through a rough surface with the coefficient of friction 0.05. What is the total distance the block travels along the surface, along the rough surface? Remember, work is equal to change in kinetic energy, which is equal to minus force of friction times distance. Now, we have not learned this equation yet. Hopefully we will in a future video. So work is equal to the change in kinetic energy. So we plug in everything we know, and we get 13.7 meters. Question 6. A mass of 2.20 kilograms is placed on a stiff vertical spring, which has a spring constant of 950 newtons per meter. The object is then pressed against the spring until it has been compressed a distance of 77 centimeters. The mass is then released and is allowed to be thrown up in the air. Part A, what will be the elastic potential energy stored in the spring just before the mass is released? 1/2 k delta x squared. Part B, what will be the gravitational potential energy of this mass when it reaches the highest point? Energy is not lost. So A and B are equal to each other. Part C, how high in the air will the mass be thrown? We're going to set the total energy equal to mg delta H. So there should be a delta H here, which I forgot. I apologize. Mg delta H. Part D, what will be the velocity of the mass just as it leaves the end of the spring? Just as it leaves the end of the spring, it's going to have this energy, because energy is conserved. Solve for V. Question 7. A vertical spring is hung from one end. A mass of 5 kilograms is hung from the end of the spring. As a result of the addition of this mass, the spring is stretched a distance of 125 centimeters. What is the spring constant for the spring? First, we need to find the force. And we're going to use Newton's second law. Sigma F equals ma. A is 0, so sigma F is 0. So Hooke's law says F equals minus k delta x. Forget about the negative sign. So we could solve for k, and we get a value. Part B, how much would the spring be stretched if the mass is 15 kilograms? Well, there's a linear relationship in this equation. So if it's 15 kilograms, we're just going to multiply this by 3. 1.25 meters by 3. The 5 kilogram mass is then lifted up until the spring is unstretched. The mass is then released and is allowed to fall until at some lower point it stops. Assume at this point h is equal to 0 meters. So how far will the mass have fallen when it stops at the lowest point? It's going to be 1.25 meters plus 1.25 meters. Because it's going to undergo simple harmonic motion. So this will make more sense when you learn about simple harmonic motion. Because when the spring was unstretched, there was no mass on it. But once you put the mass on it, it stretched a distance of 1.25 meters. So once you lift it up until it's unstretched, you lift it up 1.25 meters. Part D, what would be the GPE stored in the system when the mass is at the lowest point? Well, they're saying at the lowest point H is 0. Part E, what would be the kinetic energy of the system when the mass reaches the lowest point? At the lowest point, V equals 0. What would be the elastic potential energy stored in the spring when the mass is at the lowest point? We're going to use this equation. Part G, what would be the elastic potential energy stored in the system when the mass is at the highest point? We have 0 joules. Part H, what would be the kinetic energy of the system when the mass is at the highest point? At the highest point, V is equal to 0. Part I, what would be the GPE of the system when the mass is at the highest point? Here we go. 123 joules. What would be the total energy of the system at the highest point? 123 joules. What would be the total energy of the system at the lowest point is 123 joules. What would be the total energy of the system when the mass is 65 centimeters below the highest point? So conservation of energy is going to be 123 joules. Part M, what would be the GPE of the system when the mass is 65 centimeters below the highest point? We're going to use this equation here, mg delta H. Part N, what would be the elastic potential energy of the system when the mass is 65 centimeters below the highest point? We're going to use this equation. Part O, what will be the kinetic energy of the system when the mass is 65 centimeters below the highest point? Law of conservation of energy. Part P, what will be the velocity of the mass when it is 65 centimeters below the highest point? We have the kinetic energy from part O, so we just use that for part P. Question 8. A mass of 4.4 kilograms is attached at the end of a string, which is 2.6 meters long, is pressed against a horizontal spring with K equals 5.6 times 10 to the 2 newtons over meters as shown below. The other end of the string is attached to the ceiling. The spring is compressed by 12 centimeters by the applied force. The mass is then released and is allowed to swing outward until at some point it stops. Part A, what will be the total energy of the system just before the mass is released? So the total energy everywhere is going to be 4.03 joules. Part B, how much force is needed to press this mass against the spring? It's this. F equals kx, delta x. Part C, what will be the velocity of the mass just as it leaves the spring? Well, the kinetic energy is 4.03 joules from part A, law of conservation of energy. Energy is just converted from one form to another. The energy from the spring becomes 0 and the kinetic energy becomes maximum, which is 4.03 joules. So solving 1/2 mv squared for v, we get 1.35 meters per second. Part D, what will be the total energy of the mass when it reaches the highest point? 4.03 joules. How high in centimeters will the mass be when it stops at its highest point? So we're going to set the total gravitational potential energy equal to 4.032 joules, mg delta H, and solve for delta H. Part F, what would be the angle alpha between the string and the vertical line as shown in the diagram when the mass reaches the highest point? We're going to use this equation here, or this triangle here. 2.6 meters is the length of the string. So when it goes up, the mass, the hypotenuse is 2.6 meters. And this leg, this vertical, is going to be 2.6 minus what we learned in part E. And we could use trigonometry to solve for theta.